Hello, my name is Sai Sankalp and my registration number is 17BCE1054. This is my digital assignment 1. I'm going to talk about OpenGL. So what is OpenGL? OpenGL is basically an API. An API that is used to actually use our graphics card in order to show and render images onto the screen. It's an API, not a library. So we basically have to make calls to the the graphics card for applications to communicate with the graphic card, and so that we can utilize it in showing images. In my project I've used WebGL, which is a tool that actually uses JavaScript on the website and helps the browser to communicate with the graphic card by sending the text to OpenGL. I'm basically using WebGL. So coming to OpenGL, OpenGL is a tool. It's an API where we can communicate with the graphic card to render images onto the screen. As you can see here, this is a small representation of how things work with the OpenGL. First, we have to get the elements, that is the vertices of a particular object that we can see over here. And once we get the particular vertices, we use something known as shaders. Now shaders are basically, you can call them a way by which the graphic card actually utilizes, basically it takes the shader, takes in data and converts it into a form which can be utilized in the next stage and then can be shown onto the screen. Here we have two important shaders, the vertex shader and the fragment shader. What the vertex shader does is basically takes an element of arrays, creates a vertex array. We do this in the code using buffers. As we can see here, I've initialized buffers using the init buffer function. Let me just close this. Using the init buffer functions, that is create a vertex array and collect the data, the raw data, that is the points of the vertices. For example, in my case, it's the points of the square. Once that's done, then we actually join the points and create our object. Then we go through a stage known as rasterization. What this is basically when we create an object. It's for us right now it's in 3-dimensional form, but we are showing it in a 2D plane. So how do we put this in the form of pixels? Rasterization is the process. As you can see here, we have a cube, and this is the basic part of the cube. Now how do we show this onto the screen? Now we're basically pixelating, converting into pixels. This process is called rasterization, and this is an crucial part. Once this is done, we are using the fragment shader. What the fragment shader does is, once the rasterization is done and we have a particular pixels, we give these pixels a particular color, and the fragment shader is what it's a thing that tells what color each of the particular pixel is supposed to be. Now the fragment shader is also quite important because when we talk about lighting and shades, which are quite important in 3D objects, the fragment shader plays a crucial role in determining what color each of the pixels is supposed to have in order to achieve that effect. Once these particular pixels have achieved their color, we can show them onto the screen, and we perceive that particular image that we see to be a 3D object. This is how OpenGL works. This is a basic pipeline. To be honest, it is a lot more complex. We have tessellation, geometry shaders, and a lot of other shaders that are there, but to make it simple, vertex shader and fragment shader are the two most important shaders that are there. Another important process is rasterization, which I told you is basically, just hold on a minute. As you can see, this is rasterization. We have a triangle, and now this triangle, if I want to see it on a screen of pixels, what should I show? And this is what rasterization tells us, helps us in it. Basically it tells us what pixels we're supposed to show in order to see a particular image. we just tried a rasterization of a 3D object. So this is a nice picture. See, basically this is the scene that we create, and once we pass it to the vertex shader takes the particular points on the 3D plane and then maps it out into this form, which is, it creates a kind of this kind of structure. And once it is rasterized, that is converted into a pixelated form, which we can see, and colored, we perceived a 2D image to look more like a 3D image. The OpenGL is basically an API, and we use it in order to communicate with the graphics card or the GPU. Basically, we use the graphics card because some of the calculations and the rasterization process are a lot more faster on the graphics card than on the microprocessor. The microprocessor sometimes comes with an inbuilt graphics card, such as, for example, Intel comes with its own GPUs, and Windows has its own. There are other alternatives for graphics APIs. For example, instead of OpenGL, we have DirectX. Right now there's a new API in the market known as Vulkan, which is a cross platform, and even OpenGL is a cross platform thing, but it's not as fast as Vulkan, and Vulkan is a new open API and can be used in it. Just like we have DirectX for Windows, we have Metal for the iOS graphics API. And now let's dive into the code and see how we're actually going to make this particular shape using OpenGL. We're basically using WebGL. Now what WebGL does is basically take the code and text and pass it on to OpenGL, which later on sends this to the graphic card and tells the graphic card what to do. And once we pass the raw data into the graphic card has shaders which basically convert our raw data into a form and then pass it on to the next unit in the pipeline. Right now the two shaders that I'm using over here are the vector shader and fragment shader, and these are the base. We're only using these two right now because we're only trying to put a square on our canvas, and we don't need the other shaders. We won't be using lighting, and it's also important to note that all of this is happening in a 3D plane, and the points are being displayed, and the graphics card is doing all this using the OpenGL. Now how does the graphic card know what to do based on using the API calls? This is basically done by the company themselves. NVIDIA programs the drivers to, and so that it can understand the commands that the calls that we're sending to the API from the API, and the graphics card processes the data and returns back the output to the application, and how the application shows it onto our screen. Thank you. Hello, my name is TV Sai Sankalp Reddy, and my registration number is 17BCE1054. This is my digital assignment 1, and I've been asked to use OpenGL. So we cannot use OpenGL directly in the web browser, but there's another library known as WebGL, which enables web content use on API based on OpenGL. So basically what OpenGL does is it takes the code and runs it onto the GPU on this particular PC. Now the difference that I'm going to talk about is the difference between WebGL and OpenGL. What WebGL does is basically takes the code in the form of text, pass this text onto OpenGL. Basically WebGL consists of the control code, which is written in JavaScript, and the shader code. By shader code I mean the OpenGL SL. which is the GL shading language. This is executed on the computer graphics processing unit or GPU. So an important thing to also note here is, right now I am going to try to put a square in this canvas. We'll be using HTML canvas. Now what WebGL does is it takes a HTML canvas and gives it a 3D and uses 3D layout to actually show objects. What you're seeing here is actually not a 2D object but a 3D object. It's important to note that everything within the canvas is in a 3D space, and the shapes that you're seeing is because we're looking at a particular plane, looking from a particular plane. So let me open the code. First, let me tell you how we create the canvas. We create a HTML file, and within the body we create a canvas of a particular width and height. Now when we go to the JavaScript folder, we use normal JavaScript to actually create an object canvas by using DOM, and here we use getContext and assign it to the variable GL. Now what we're doing here is, first we check whether our browser supports WebGL or not. If it doesn't, then we get an alert. Now as you can see here, GL is the canvas, and we put a color of 0, 0, 0, which is basically an RGB color with opacity 1, and we clear if there's anything in the buffer. This gives us the canvas. Now let us go into how this particular shape is being rendered. So now let's see how this is being done. Now as I've told you that we're doing this in the 3D plane, that is an important point. Now let me talk about the shaders. A shaders is a program written using the OpenGL shading language. Basically there are two shader functions we use, that is the vertex shader and the fragment shader. Together a set of vertex and fragment shader is called as a shader program. Now when the shape is rendered, what the vertex shader does is it takes the point, the input vertex from its original coordinate system and puts it into the clip space coordinate system, which is being used by WebGL. What this is basically each axis has a range of -1 to 1, regardless of the aspect ratio, size or any other factor. This is the code. This is the vertex shader program, and this is the fragment shader program. As we can see here, this mat4 is nothing but a matrix of dimension 4, and vec4 is a vector of dimension 4. These three, the vertex position, the model view matrix, and the projection matrix, are important factors that determine the position. Using these three variables, we can determine the position. The vector source is more focuses on the vertex shader is more deals more with the way the object is positioned and how each and every vertex is represented on the clip space whereas the fragment shader deals more with lighting and texture. For example, once the image is being placed or positioned within the space, each and every pixel has a particular amount. The color of each and every pixel is determined by the fragment shader. This is quite crucial when it comes to lighting. These two sections are quite important. This section is actually how where we get the particular variant, where we get the vertex position, projection matrix, and model view matrix, and we are actually collecting all the info required by the shader program. Now the shader program is a combination of two shaders, that is the vertex shader and the fragment shader. We are initializing the shader program using the command init shader program or initialize shader program, and we're taking the canvas, we're taking the two shaders and combining them to create a shader program. Once we do that, we are gathering all the info we require to for the program. Now this is the main function, draw scene. This is the one that's responsible for drawing the square in our particular code. Here we have used init shader program. Let us talk more about this function. The shader program tells the WebGL how to draw the how to represent our data. Here we are creating two objects, shader objects, one which is the vector shader and the other one which is the fragment shader, and we are linking the two informations that we are given here. Now it is important to know that these are text. This text is being passed, which is basically OpenGL text, is being passed into WebGL so that it can be compiled directly on the GPU. Now since we have created two objects for the shaders, now we are going to take these two shaders and we are going to attach them to the canvas. First we're going to have to create this shader program by using the create program function. Once we do this, we are attaching the two shaders to the program and then we link them together. Then it is important to check whether the shader programs have linked or not. So therefore we are creating a function here to check it. That is the link status. If the link has not been established, then we get an error and we return a null for the main function, and hence nothing happens. Else we return the shader program. The shader program is sent here. As you can see, this is where we sent it, and we have used this in our program info. The next function, another important function, is init buffer. What we're doing here is storing the particular buffer data that is required for the square or the box. We're storing its positions. We are basically we are storing the positions of the box and returning it to this constant buffer over here. This buffer is later on being passed into the draw scene function, which is our main function. Now let's talk about the draw scene function. We have passed the program info and the buffers, and we passed G1, which is the canvas. G1 is actually the canvas. We've got the context. Now let's go back into draw scene. We have created a black color, fully opaque. Then enable that function. We use the g1.clear function to clear all the buffers that are already there. Now we're defining the perspective matrix. It is the matrix. Now let's talk about the perspective matrix. We are creating the perspective matrix, which basically a special matrix that tells us how we are that basically determines our field of vision, width and height ratio, display size, and we only want to see objects between 0.1 units to and 100 units away from the camera. That is what Z near and Z far is. So, and then we have a projection matrix and we create it. Now in the projection matrix we add all these values and create a matrix for perspective. We are using a helping library glmatrix.js. What the draw function does is, once the shaders are established, the locations are looked up and the square, planes, vertex positions are put in the buffer. Now that we have described the scene, we have to render it. The first step is to clear our canvas, as we have done here. To our background color that we establish the camera's perspective. Now that we have actually cleared it, now we are setting the perspective, and the perspective is setting it as 45 degrees with a width and height ratio that match the display dimensions of our canvas, as we've done here. That is where this is the width to height. We also specify that we only want objects between 0.1 and 100 units from the camera to be rendered. Once the perspective matrix is designed, then we move on to the translate. Now we want to determine the identity position to start drawing our square. To do this, we have to move the identity position and translating it away by 6 units. After that, we bind the square vertex buffer to the attribute the shader is using. That is the vertex attribute pointer, a vertex position. And we tell WebGL how to pull the data out of it. Then we finally draw the object by calling the draw arrays method. This is the draw arrays method. The draw arrays method is what we're actually using to, this is the function that actually puts stuff onto our canvas. Now the init buffer, as you can see here, this is what actually creates our square plane. Before we can render our square plane, we need to create the buffer that contains its vector positions and put the vector positions in it. So we have to group them and then we have to put them inside. How do we do this? We do it all using the init buffers function. The routine is pretty simplistic given the basic nature of the scene. It starts by calling g1 object create buffer. This is where now we created a buffer named position buffer, and once we've done this, we actually bind this to an actual buffer, g1 array buffer, using the bind buffer function. The position contains the positions of the our object or the square. Now that now the buffer has been binded, we use that buffer, we use positions, convert it into a 32-bit float value array, and we're actually storing it in this. Then we return the positions with the position buffer that we have created. The load shader function takes as input the WebGL context, that is G1, the shader types, and the source code. It then creates and compiles the shader. It does it through few steps. First, it uses the create shader. A new shader is created by using this function. Then the shader source code is sent to the shader using the shared source. Once the shader has the source code, it is compiled using the compile shader. To check to be sure the shader is successfully completed, we use this particular function by using the G1 compile status and the get shader parameter. Basically, this is a parameter, and using this we can get it, and now we're going to use it to check whether the particular process has been completed successfully. Only if all this, and only if the status is complete, shows is a positive status, then we return the shader. Now it is important to know that unless the load shader is called, our code is being compiled, but it is not being displayed or not being executed. As you can see, this is the result of the code. I wanted to tell you that we were using WebGL, which actually utilizes the OpenGL SL to display this particular shapes over here. We have a lot of libraries that use WebGL and OpenGL to actually do graphics manipulation in canvases. One of the famous libraries is p5.js, which I recommend, and is very easy to use. As you can see, the code is quite cumbersome. By because you have to create vectors, matrices, store the positions, uh, determine the perspective array, perspective matrix, and then using all these we're going to have to use shaders and load items onto the canvas. This is quite a complex and cumbersome process, and we have higher level libraries that can simplify this. One of the libraries is p5.js. Sorry. It is really easy to use this particular library to achieve what we just did in our particular code. For example, if I were to take 2D shape square, this is all that is required to draw a 2D shape. p5.js was built over OpenGL and WebGL. Thank you.